Hello, I am Tuhin Mukherjee from Pennsylvania State University, and I would also like to acknowledge my co-author, Professor Tarashankar Debroy from Pennsylvania State University. Additive manufacturing of high-quality parts in one go is a difficult task. Trial and error optimization of process parameter to achieve high quality will not work for additive manufacturing because it is time consuming and expensive. So in this talk, I am going to tell you how machine learning can help to achieve high quality in additive manufacturing without doing trial and error, and how it can improve the quality consistency and cost competitiveness in additive manufacturing. So in my talk, I am going to talk about uniqueness and opportunities of additive manufacturing and why we need machine learning and how mechanistic model can support. So essentially, I'm going to give you several examples of how machine learning can be used to reduce some of the common defects like cracking, lack of fusion, residual stresses, surface roughness, etc. So additive manufacturing is very unique process. For example, in International Space Station, they needed a range, and that time NASA did not have any plan for supplying essential things to the International Space Station. So what they did, they essentially sent an STL file of the range from the Earth to the International Space Station. And in the International Space Station, there was a 3D printer that actually printed the range. And you can see in this picture that the astronaut is holding the actually 3D printed range. So even 30 years ago, it was a science fiction, but now, because of the additive manufacturing process, these unique things can be achieved. At Penn State, we have shown that the creep life of dissimilar joint between a steel and a nickel alloy 800H, which is commonly used in nuclear power plant, can be significantly improved if we can replace the dissimilar joint by introducing a graded joint manufactured by additive manufacturing process. In Auburn, Alabama, GE is printing aero engine fuel nozzle, which was traditionally used to be made by joining several small components. So because they are printing these nozzles in one go, it is improving its reliability and safety in the operation. And you can appreciate the market penetration of additively manufactured component because the revenue is coming from different industrial sectors like automotive, medical, aerospace, gas turbine, so on and so forth. So what exactly the problem? To me, the problem is we still do not control the defects properly. And this is very evident that we have more than 5,000 commercial alloys. And how many you can actually print? You can probably count with your two hands. So the common defects that create the problems are lack of fusion void, residual stress, cracking, surface roughness. These are the defects. And trial and error adjustment of process variable to avoid these defects, like what we were used to do for traditional manufacturing processes like casting and welding, will not work because of two reasons. First, the machine is expensive and feedstock is expensive. And second, in the left hand side, you can see that the process parameter range vary a lot. Even for the same alloy, depending on which additive manufacturing process we are using, the power, speed, deposition rate, layer thickness, which are the essential processing parameters, vary a lot. Please note that these plots are made in logarithmic scale. So depending on the process parameters, several order of magnitude of the scanning speed can vary. So, how machine learning can help? So, we do not need a phenomenological understanding of the formation mechanism of those defects. If high quality data are available, we can process those data using different types of machine learning algorithm to figure out what works and what does not work. So let's say we are using a neural network based machine learning which is trained to predict the fusion zone depth based on the process conditions. And when we have a trained neural network, it can tell us that what would be the conditions necessary to achieve a required depth, which is actually essential for controlling many defects such as lack of fusion, distortion, so on and so forth. So, machine learning in additive manufacturing can be very easily done because of the availability of several open source codes. So I have provided a list which I have taken from one of our recent publication published in Nature Reviews Materials, which is the highest impact factor journal in the physical sciences. So there we have used this table where we have shown that there are several open source programs for machine learning, and these programs are extensively used in additive manufacturing. But machine learning needs a lot of data. What if you do not have those data? What if generation of such data is cost prohibitive? For example, in additive manufacturing, since this is an expensive process, generation of high volume of high quality data is often cost prohibitive. So, what to do? One recourse would be to teach machine learning the physics of the problem. How? If we have a mechanistic model of additive manufacturing process, we can essentially calculate the variables that are most important for a problem and use those variables to train the machine learning. The machine learning will not only perform reliably with the less amount of data, but also it can provide us the hierarchical importance of important factors so that engineers can know which variables to tune in to get a good quality part. Now, let me give you several examples of that. Let's say we talk about cracking, which is one of the most important problems in additive manufacturing, especially in the additive manufacturing of aluminum alloys. So here I have put several variables like laser power, laser beam radius, scanning speed, so on and so forth that affect crack formation. So precisely there are 12 variables, and if we follow a two-factor design of experiment, the minimum number of experiments that we need is more than 4,000. And even if you do one successful experiment a day, you need more than 10 years to gather the data. So that's not feasible process. So what we can do, we identify the most important physics-based variables that control crack formation. For example, cooling rate, ratio of temperature gradient to solidification growth rate that controls solidification morphology, ratio of vulnerable and relaxation times that tell us how crack may form during solidification, and solidification stress that actually initiate and propagates crack. So these four variables, if we can calculate using a mechanistic model of additive manufacturing, you see that it needs a minimum of 16 experiments following design of experiment, and we can get an idea of what works and what does not work. What are the benefits of that? Based on these four variables, using machine learning, we can derive a simple, easy to use crack susceptibility index. And you can see that here we have more than 100 data points for three commonly used aluminum alloys, and these crack susceptibility index actually provide a delineation that can correctly separate the experimental cases where cracks were observed and experimental cases where cracks were not observed. So you see that if we can correctly use machine learning, it can give us some verifiable user-friendly index that can be used to prevent crack without doing trial and error experiment based on scientific principle. So we can print crack-free part in one go. The second advantage of this kind of analysis is it can provide which variables are most important and which variables are less important. For example, here we have used two different types of machine learning algorithms, information gain and information gain ratio, both of which actually told us that solidification stress is the most important factor causing solidification cracking in additive manufacturing. So the advantage of this type of analysis is to know which variable you need to adjust before doing experiment, so that when you can go to the shop floor and do actual experiment, you can print a crack free part without doing many time consuming and expensive trial and error. Lack of fusion void is another problem in additive manufacturing, and this is a typical example of molten pool that happens during the additive manufacturing process. If you look at the transverse section, you can see the transverse section of the deposit, which looks like half of a watermelon. Now, as you know, in additive manufacturing, a real part is made by depositing many such hatches and layers. So if we stack them together, you can see the white region between several deposited hatches and layers. These white regions are the source of lack of fusion defects. How do you minimize that? Intuitively, you can say that if we bring these two watermelons close by, then the white region will disappear. We call that distance as hatch spacing, as you know. So if we reduce hatch spacing, definitely lack of fusion defects will be reduced. And when we go to the shop floor, do the experiment, we exactly find the same thing. That means to avoid lack of fusion defect, we need to print a part with less hatch spacing. There are also other ways of minimizing lack of fusion defect. If you scan slowly, that means you are depositing more heat per unit time. That means you are melting more material and the size of fusion zone is bigger, and that will actually eliminate the unmelted region between two consecutive tracks and reduce lack of fusion void. For example, you can see here, if you reduce the scanning speed from 1000 millimeter per second to 250 millimeter per second, the lack of fusion defect is significantly reduced. And that is consistent with the experimental observation where scanning speed was reduced to reduce the lack of fusion void fraction during the laser assisted powder bed fusion of stainless steel 316. So if we process all the data and all the knowledge using machine learning, it tells us that among all variables, there is one variable that is the most important factor. That is the pool width to head spacing ratio. So pool width is the width of the fusion zone or molten pool, and hatch spacing is the distance between two neighboring tracks. Their ratio is the most important factor. And here you can see that there are 120 data for four commonly used alloys for additive manufacturing, and these variable can delineate the cases where lack of fusion was observed and good cases where lack of fusion was not observed. And when we go back to the shop floor and do the experiment, we can exactly find the truth of the delineation. So essentially, this kind of analysis is telling you that what you should do before doing the experiment, so that when we go to the shop floor and do the experiment, we can print a part without lack of fusion defect in one go, without doing many trial and error. Residual stresses can be calculated using commercial packages like Abacus or ANSYS. But one challenge that we often face using those software is they do not consider the effect of convective flow inside the molten pool while calculating the temperature field, based on which they calculate the residual stresses. So what we did, we developed a heat transfer fluid flow model of additive manufacturing process that considers the effect of convective flow inside the molten pool and accurately calculate the temperature field. We use that temperature field, import that in a commercial package, Abacus, to calculate residual stress and distortion. And what is the benefit? You can see that the computed results are consistent with the experimental observation. Here are the two examples. In the left-hand side image, the residual stress is taken along a line A to B along the substrate deposit interface. And in the right hand side image, the residual stress is taken along the vertical direction from C to D. In both cases, we have considered the through thickness component of the residual stress, which is the vertical component of residual stress. And you can see that for both cases, the computed residual stress matches reasonably well with the experimental result. And you can appreciate that this kind of model can be very reliably used to compute residual stresses for same material for different processes and for the same process but for different materials. So here for stainless steel 316, you can see that in DDGMA, where we deposit a lot much more material during the deposition process, it accumulates a lot more residual stresses. But in powder bed fusion, where we deposit thin layers, often thinner than human hair, the accumulated residual stresses are much less. Similarly, if we process Inconel 718 and Ti64 using the same process and same processing condition, you see that since titanium alloy has higher yield strength, it accumulates higher residual stress. When we use this computed residual stress in machine learning, it tells us the temperature gradient is the most important factor. And you can see the variables are used in a random forest model based machine learning, and we have 243 data for three different alloys. And if we combine all these things, it can tell the difference between the solidus and preheat temperature is the most important. And this is very consistent with industrial practice, even for fusion welding, where we increase the preheat temperature before doing the welding so that we can reduce the temperature gradient to control residual stress. So data analysis using machine learning can reveal us very important insight. Surface roughness is another problem in additive manufacturing. So here I give a very interesting example of printing a robot where you can see that same material, same part can be printed using two different layer heights. If you use 200 micron layer heights, you can finish the component faster. But look at the surface, they have staircase effect. That means the surface quality is not good. It needs post-processing like machining, grinding, which will add extra cost. But you can print the same component using thinner layer like 100 micron thick. Probably it will take more time, but you can print a component in one go with very smooth surface. So if you want to achieve good surface finish, you need to print the part using thinner layer. GE prints their fuel engine nozzle using very thin layers, often thinner than human hair, to avoid such problems. So essentially, uh, what we did, we found out the most important variables that control surface roughness, and I have listed this variable here, and combine this variable to find a dimensionless index that we call surface roughness index. And you can appreciate that we gather 126 data for four different alloys that are commonly used in additive manufacturing. And you can see the experimentally measured surface roughness follow a linear trend with the index. So what is the benefit? This kind of index can tell us which parameter set you need to use to print a part with low surface roughness, so that when you do actual experiment, you can print a part with very smooth surface in one go. Balling formation is another problem that can create surface roughness. So essentially it forms small metallic balls that will eventually solidify and create discrete island on the surface of the component and results in rough surfaces. So if we process several data for different commercially used alloys in additive manufacturing, and here we have 105 data. You can see machine learning tells us that Marangoni number and solidification time are the two most important variables controlling this defect. Marangoni number that tells us how rigorous the convective flow is, that controls the shape and size of fusion zone, and solidification time that essentially denotes the life of the molten pool. So these two are the most important variables, and you can see that these two variables can delineate the data based on whether balling occurs or balling does not occur. So to summarize, the main contribution of this work is essentially the emerging digital tools such as the machine learning, and when we teach machine learning the physics based on the computed variables using mechanistic models, and that we call as physics informed machine learning, can solve many important problems in additive manufacturing. For example, crack formations. So I have here provided several examples like lack of fusion defects, residual stresses, cracking, surface roughness, so on and so forth. And you can see that these emerging digital tools can provide pathways to control these defects. So use of these digital tools can actually help in improving quality consistency and cost competitiveness by reducing the trial and error process, accelerating the part qualification for additive manufacturing processes. So that's all from my side. Now I would be very happy to take any question from you.